Recording is rolling. It is Tuesday, September 17th. Today's going to be a lab day. I did preview this with you guys yesterday. We're moving on to forces and Newton's laws of motion. Good. I like to kickstart new topics with labs if I can a lot of times. So you guys get to get your hands on the equipment and materials and play it out. And then we guys see the textbook questions like, oh yeah, that's exactly what we did in the lab. Kind of thing. Okay? So here, I'll remind you guys some stuff about this. But before we get to the lab today, a couple other things. One is check focus. This class, also all your other classes, make sure you're getting everything in there. You're not missing any assignments. I've had a number of students so far this year thought they turned something in. It's not showing up in the grade book. Oh, actually, it's down this folder. Oops, I never turned that in. So yeah, make sure you're not missing anything. This class, other classes too. Okay. We're gonna do a teacher of the year ballot. So I got this ballot in my school box this morning. Right, for vote for teacher of the year, vote for employee of the year. We're just gonna focus on teacher of the year. I always take this opportunity every year to talk about election systems with students. There's a science of election systems. There are different rules you can have for different types of election systems. So here, let's do this. Take pause here. All right, so and depending on what the election rules are, you can get different outcomes. You might have a list of candidates. In this case, we got these 4 candidates. Here, let's look at these. I got Mr. Egan, Ms. O'Boyle, Ms. Wayne, Ms. Winston. I want you guys to think in your mind who you would like to be teacher of the year out of those 4. And then I'll check one of these boxes and submit this to admin. But I wanted to pull all my classes first. Okay, so you can have different election systems, and different election systems can result in different winners. So just for this lesson, I want to just narrow this down and focus on these 2 types of systems. One called first past the post, also called plurality voting. And I want to contrast that with a different system called, you can also rank your choices, and then there's different ways to tabulate the rankings, but we're going to look at one specific process called instant runoff. Okay. All right, so let's start with the first one. First past the post, plurality voting. Guys, what is that? I bet somebody knows. What is plurality voting? How does that work? How about this? Just a normal, let's say American ballot, because different societies use different systems too. But in the States, we tend to use this one, first past the post. So suppose you got a ballot with 4 candidates on it. How many do you bubble? Just 1, right? So you bubble 1. Right? Now I'm just gonna make up some numbers. We'll do a simulation here in a few minutes. We'll see how this actually plays out in class. But let's say, for sake of argument, suppose it goes like this. Maybe Mr. Egan gets 5 votes, and then Ms. O'Boyle, let's say, gets 3, and Ms. Wayne gets 3, and Ms. Winston gets 2. It's 5 to 3 to 3 to 2. Guys, 5 to 3 to 3 to 2. Who got the majority? What's the definition of majority? Like more than half, right? More than half, right? So did anybody get the majority? No. Mr. Egan would have the most votes, and I just something I made up. So he wouldn't have the majority. He would have the what? Plurality. Right? And if you go by this set of rules, then it's just whoever gets the most votes wins. That's it. So in that case, my just made up example, Mr. Egan would win that, right? But wait a minute. He didn't actually get a true majority. So what about students who were voting on these other 3 teachers? What if they all kind of like, what if all these other teachers have sort of a similar teaching style, for example? So like, okay, well, if you like one of these, you kind of like all of them. Mr. Egan's got his own thing going on over there. It's totally different. Okay? You guys see that there's like vote splitting going on, sort of, right? So how this kind of carries over to say like a government type election is, what if the analogy is, what if it was like an ideological spectrum and you got one candidate on one end of the spectrum and then like 3 other candidates that are pretty close to each other on the other side. Okay? Well, they might have small differences, but if they split the vote, you guys see, it's called the spoiler effect. That's the term for it. It's called spoiler effect. Okay? By running in the race, you're actually in the large field of candidates, you would actually be hurting your own ideological interests in your own platform by having a similar platform to other candidates that you're drawing votes away from. Okay? And so that's a downside. And then as a voter, well, now you have to engage in what's called strategic voting. So it's not just who do I really like the most. Well, now it's okay. Well, who's everybody else voting for, and I have to change my vote based on that. And so there's some problems with that. There is no perfect voting system. There was some math work out in 1950s, something called Arrow's impossibility theorem. Any system you look at has some downside. There's some weird situation that can come up, some downside. Okay? But there are better and worse voting systems. So here's an alternative here. What if instead of just picking one and walking away, what if you could rank your choices? And by doing that, you can actually supply more information on your ballot. So you could rank somebody number 1, but then you could rank somebody number 2. And then if you like, you could rank as many or as few as you want. You could rank number 3 if you want, right? Now, if you want to rank all of them, you can rank all of them. And what that'll do is if there's no majority, well, if there's a majority, then they just win anyway, but they would have won anyway under any system. But if there's no majority winner, then now you can process these votes in a different way. Now, in instant runoff, the technique is that you drop the candidates with the fewest number one votes and then say, okay, well, who were those voters' second preferences, right? And then you do a bunch of iterations until you actually do arrive at a majority. You guys can get that, right? There's other ways to tabulate ranked choice. Also, there's a method called Condorcet, which is really good, but it's a little bit more complicated. All right, so you guys ready to vote? You guys ready? All right, so I want you guys to think in mind, who's your number one choice? And then we're gonna use this ranked choice type method. So if your number one doesn't win, then who's your number two? And maybe even who's your number three? Right, you guys got out of these four candidates right here, right? You guys got somebody in mind? We're gonna do a hand count just to move this along kind of fast. And so I got you guys queued up right here. Got period 7. You guys can vote. Okay, got Egan, O'Boyle, Wayne, Winston. Right. So guys, remember as we're doing this, whoever you like the most, go ahead and vote for them. Even if you're the only voter voting for that particular teacher, that's okay. You're never throwing away your vote with this ranked choice method that we're going to do. Right now, first past the post, you do have to worry about that, right? But not ranked choice. Ranked choice, you can express exactly what your preferences are, and then if they don't win, then you just bump to your second choice. Okay. All right. You guys good? Okay. You guys ready? All right, here we go. All right. So we're going to go down the line. So raise your hand, look for just first place preferences. So who's your favorite? I bet you have one favorite out of these four. Here we go. Who's voting for Egan? Votes for Egan. Go ahead. Got 1, 2, 3, 4, 5. All right. So it's like 5 votes on Egan. All right. O'Boyle. Let's vote for O'Boyle. O'Boyle. All right. Gets a couple of votes on O'Boyle. 2 votes on O'Boyle. How about Wayne? He's voting for Wayne. Got 1, 2, 3, 4, 5, 6, 7. So, all right. So 7 votes on Wayne. How about Winston? He's voting for Winston. Winston got 1, 2, 3. All right, 3 votes on Winston. All right. Ooh, actually, this is playing out pretty good because I'm able to definitely make my point with this. All right. So, guys, all right. So. Right now, who wins? It really depends on what set of rules we had from the outset. Okay, guys, who would win this race if we had first past the post? Who would win? Yeah, Wayne, because plurality, that's the most votes there. Right? But who has the majority? Nobody. But see, we don't know what the second preferences are from these other voters, right? But we're about to find out. Right, guys, see this? Right. So I can definitely strike O'Boyle. Tell you, just to move class along a little bit, I'm gonna. Suppose if we had another iteration, technically you would do an iteration at this point, but I'm going to go ahead and strike Winston just to move us along a little bit. Let's narrow it down to Egan or Wayne, because either of them could possibly be a would. All right, so you guys ready to do like a round 2, or actually a round 3, I guess at this point would be. You guys ready? You guys ready? Okay, here we go. Who's voting for Egan? Votes for Egan. Got 1, 2, 3, 4, 5, 6. All right, 6 votes on Egan. All right, let's vote for Wayne. Who's voting for Wayne? Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's like 10, I think, like that. All right. All right. Yeah. Okay, that looks pretty good. And looks like we lost a vote overall, but that's okay because maybe somebody voted one, but never ranked anybody after that. You could do that too, right? Okay, so now we have a majority. Now we have like a true majority. So I'll say point Wayne could be the true winner. Right? All right. So you guys see that? All right, so there you go. There's how you do ranked choice a little bit. All right, guys, let's move on to today's lab. Okay. So we're moving on to forces and Newton's laws of motion. I want you guys to do 10 mini labs. You might not get to all of these. That's okay. I'll help you guys out with these. Okay? And you're measuring what are the forces in, say, like each of these scenarios. So you guys are going to get some spring scales. Now, these spring scales, so look at how they work. Oh, see, on one side, it says capital N. Guys, what is capital N as a unit? What does that stand for? Newtons. And look how it's scaled. 0, 2, 4, 6, 8, 10. Right? Now, if I flip it over, I got, do you guys think lowercase g stands for grams? Right. Guys, are you going to record anything about grams on with the spring scale? No, that's just like what mass would produce, what weight, and Earth's gravity field. I don't care about that. I care about Newtons, right? I apply some force. Guys, all force is just a push or a pull. There isn't pulling. There's a tension force. It's stretching the spring. And the fact that it's scaled linearly, 0, 2, 4, 6, 8, 10, means like if I apply some force, it stretches some amount. If I double the force, it's double the stretch amount. If I triple the force, it's triple the stretch amount. You guys see it's a linear relationship between how much force I apply and how much it stretches? That is called Hooke's law. Look at that. To stretch some amount, it requires some force. To stretch twice as much, takes double the force. You guys see that linear relationship? Now, don't worry about the green triangle yet. We'll save that for a few weeks from now. That's like, I ate my Cheerios this morning. Now I have the energy to pull it. I didn't eat any Cheerios. I don't have the energy. But now I can pull it. Take some energy. Right? We're not focused on that yet. That'll be a few weeks from now. So ignore the green triangle for now. Just focus on this graph itself. This line, right? Linear relationship. Now there are different scales. The brown one's kind of the middle one. That's probably the most useful one. But look at this green one, guys. Little tiny force. It's really easy to stretch this guy. Little tiny force stretches a huge distance. Could that also be, it's still scaled linearly, but little tiny force stretches a lot. Hey, could that be like a really shallow line like that? You guys think? Okay. Versus if you break out the gold one, this one's a little messed up. You guys got a big old thick spring right there, big old thick spring. It goes up all the way to 50 newtons. It's a huge force. It's really hard to stretch it. So a huge force only stretches it a tiny bit. That could be like a point way up here. Right? And then it's also scaled linearly. So do you guys see 1, 2, 3 different graphs, 3 different slopes? Right. That's what this equation is. F equals kx. F is how much force. X is how much it stretches. What's k called in physics? The spring constant. Spring constant. These have three different springs. Okay, you guys good? Good so far? Right. And on the graph, of course, that's the slope of the graph. Okay. Here's unstretched spring. Here's a stretched spring. You might see a compressed spring, although these aren't compressible springs, but if you did, that could go the other way too, right? All right, so I get some common questions about some of these scenarios, so help you guys out here. The very first scenario, can you guys put different masses on this and say how much do they weigh? Do you guys think weight is a type of force? Right? Weight's a type of force, you can quantify that in newtons. So as you have increasing mass, it's because you have different masses. It's going to weigh more, but you have probably I bet you have a pretty good guess what that graph's going to look like. Right? Weight versus mass. You say. Right, the second one. Oh, guys, do you see 2 spring scales right here holding up 1 lab weight? Okay. I want you to shift it back and forth. Do you think you can shift it a little bit so you can put more force on one, more force on more force burden on the other? Shift it right, left. Right? What's the force on the left scale? What's the force on the right scale? What's the total force? And if you graph the left force versus the right force reading, remember, you're using the same weight over and over and over again, but you're just shifting more weight to the left or to the right. Can you plot those coordinates? You have some Cartesian coordinates here. Can you plot those? What's that going to look like? Right? The third one, in 2 dimensions. So you guys see you start at vertical and you start spread out like a Y and then make it closer to a T shape. Okay. So I want you to record what angle is this from the vertical. Guys, you see this vertical dashed line right here? Notice this angle with respect to the vertical. So I'm going to take this protractor. There's some protractors back there. Take this node, put it right in the middle where all 3 come together. Okay, and then notice how I'm holding this. So the vertical line is zeroed out. You see that? And maybe one of these spring scales like sweeps through some angle, so many degrees. Like this one looks like about maybe like 60 degrees. About you guys think maybe about like that? Pretty close. All right. Now, do you guys see how they're all symmetrical all the way down? In this table, it says what's the force on the bottom spring scale. So this bottom scale. What's the force of each top one? If I made this a little bit more scientific, maybe I should do this. Maybe I should split the cell in half so we can record the left and the right. But I mean, if it's truly symmetrical, like horizontally symmetrical, do you think ideally they should read the same number? Do you guys think? Right. So they should be pretty close. So you can either split the cell or take the average, or maybe they're just saying the same number anyway. Okay. Right. Can you plot that? Right. So angle, force reading, and each top spring scale. So here's this angle. See this angle from the vertical. It looks like I'm trying to make it closer and closer to a T shape. If I had a perfect T shape, what would this angle be from the vertical? This is a perfect T. How many degrees? 9. It would be 90. Hey, the graph only goes up to 90 degrees. You guys see that? All right, that'll get the ball rolling. Go ahead. Everything you need is back in the lab area. You guys have spring scales, lab weights, protractors, string. I'll be walking around helping you guys out. If you don't finish the whole thing, that's all right. Just turn it into the gray tree at the end of class, and as long as you guys are working, then you get credit for the lab.